Okay, let's look at a resistors and parallel question. So let's do those same resistors, but let's put them in parallel this time. So 1, 2, and 3. So we have 6 volts, 100 ohms, 500 ohms, and 300 ohms. So 100, 500, and 300. So this one, we know current is going to be drawn from the battery. And when it gets to this junction, that current I is going to split into two. So some of it's going to go down, call this I1, and some of it's going to go to the right. When it gets that current, it gets over there, whatever was left over is going to split off into these different directions as well. I2 and I3. You may ask, like, why didn't I draw anything in this space right here? Like, why didn't I define this as some current? That's because I could have also drawn, there's no resistor in there, so it's kind of pointless. Because I also could have drawn like all three of those at that point. So you could have had, say, I going in, then I1. But then instead of drawing a nice box, I could have had like two paths like so. So it's the exact same circuit. It's not as nice though. But it gets the same point. So it just all connects to that single junction. But instead of just 1 in, 2 out, it has 1 in, 3 out. Okay, erase that. Okay, so how do we solve this? We're going to use this other equation. So we get 1 over RT is equal to 1 over R1, so 1 over 100 ohms, plus 1 over 500 ohms, plus 1 over 300 ohms. So this is equal to 1 over RT. So if I now take this and to the power of -1, that will give us our RT value. Plug all in, we get 65 ohms. So what this means is if I had a circuit with just a single resistor, that resistor would have to be 65 ohms to get the same current draw. 6 volts, and now we can just say, okay, what's 6 volts divided by that 65 ohms? So I is equal to V over R, RT. So you get 6 volts over 65 ohms. We get a current draw of 0.092 amps. Okay. Now for circuits in parallel, the voltage drop has to be the same across each thing. So in series, the current is the same. Let's draw that out. So for series circuits, the current is the same through all of them. So I is the same, but the voltage drop is different. For parallel circuits, the current is different. We can see I1, I2, I3, assuming that they're not identical resistors. If they're not identical resistors, then current split is going to be equivalent. But assuming they're different resistors, current is going to be different, but the voltage drop has to be the same, because if we follow any path around the circuit, so if I look at this loop, the voltage must sum to 0. So I'm getting gain 6 has to do 6, gain 6 has to do 6. If I follow this path, gain 6 to do 6, gain 6 to do 6. Or I follow this one, gain 6 to do 6. It doesn't matter. So voltage drop in parallel is the same. So if I look at I1, if I want to find I1, that's going to be V over R1. So I already said that we know it must be 6 volts across I1. So divide that by 100 ohms, you get 0.06 amps. If I look at I2, that's going to be 6 volts over 500 ohms, which is equal to 0.012 amps. And I3 is equal to 6 volts over 300 ohms. It's equal to 0.02 amps. So you see I think I mentioned previously, but current wants to travel the path of least resistance. So because the 100 ohms is the smallest of those three resistors, clearly we can see there's more current passing through. And notice if we add up all those values together, 0.6, 0.72, 0.06, 0.072, 0.092. That all adds up to 0.092 amps. Okay. Current in, 0.092. Current down each individual path. They add up to the same value. So if you actually were interested in what the current would read right here, and this spot right here, on that wire, if I1 was 0.06, that means in that path it would be that 0.092 minus 0.06, 0.032 amps. And that 0.032 amps split up into the 0.012 and 0.02.